but if you go to the website, no, in North America, the prices are a little lower, I think, than here. But if you go to the website, there's often sales because they make 20 filters at a time. So if you want a filter, you say, I want a filter, and they say, okay, that's $2,000, but they make 20. So if you go to their website and you go for the sales, then they still have 19 filters that they have to sell. And sometimes you can get them for $50. So.
Okay, that was a big
yeah. And since these filters are used by very advanced physicists, they also not just biologists, you can often get a very good filter for very little money because they got to get rid of them. So most of the filters I buy are about $200.
Sorry.
Yeah.
I will stop a little bit here, but be sure that everybody understood it because this is very important. How the system works. Yeah. I would like to check that everybody understood that.
Okay. Why don't you step up here and
No,
I'm serious.
Okay. ¿Todos entendieron esta parte? ¿Por qué? Mira, ¿por qué esto es? Esto es muy importante porque de esto depende la investigación que ustedes van a hacer y cómo ustedes van a discriminar y detectar las células. Por ejemplo, claro, usted tiene un objeto de onda, pero aquí hay una serie de filtros y arreglos, digamos, que son, bueno, como decía, cromáticos, en el cual ustedes dejan pasar una luz o no dejan pasar una longitud de onda. Por ejemplo, ¿entendieron, por ejemplo, como lo que explicó los 650? Esto significa que deja pasar solamente todo lo que sea superior a 650, ¿cierto? Nómetros de luz. Entonces esto es muy importante porque aquí de esto ustedes van a tener los diferentes detectores. Uno para acá, para la ficoditrina, uno para la clorofila o para la ficocianina. Entonces por eso es súper importante que entiendan bien este arreglo porque de esto va a depender ustedes después cómo discriminan las células que van a objetivo. Ya sea la inversión que hagan ustedes o en la parte natural que digamos ahí donde se hace más interesante y que te permite, por ejemplo, tener una mayor cantidad incluso de láseres y de detectores para poder discriminar, porque a lo mejor un grupo que tú ves agrupado como un clúster solamente o una regla celular, eso tú lo ves de otro lado y ves que no había uno, sino que habían dos. Y de eso va a depender, digamos, este arreglo. Por eso es muy importante que entiendan bien que este tipo de arreglos te permite a ti después hacer investigación y te permite después discriminar. Incluso tú puedes después comprar tu filtro de acuerdo a tus necesidades o de acuerdo a las tensiones que tú estás haciendo. Porque I'm not so sure, but if you can change your range of pitches, right? Okay.
No, this is a very important point.
Yeah. Entonces ustedes ahí se pueden cambiar, ¿sabes qué? Este no lo ocupo yo y lo cambian. Entonces lo ocupan por ustedes. Por eso es que es importante que entiendan bien, pueden leer un poquito más en todo lo que es filtros, porque ahí van a tener un poquito lo que es de paso bajo, de paso alto, o que unos que reflejan, entonces de eso va a depender, digamos, como les digo, lo que ustedes quieran hacer. Por eso, ojo con esto, porque aquí está la base un poco de cómo funciona el equipo, y de lo que ustedes después van a ver, porque ustedes van a ver puros puntitos, después no van a ver el dibujo, van a ver puros puntitos, entonces tienen que entender bien de dónde vienen esos puntitos, o sea, qué filtro están ustedes usando dentro del arreglo que ustedes tienen. Así que eso es importante, porque no todos los citómetros tienen el mismo arreglo de filtro. Por ejemplo, el de...
I think that total flow cytometers can change the filters, yeah.
Okay.
In most of them. And it is so important because your manufacturer will say this is a red filter. Mm-hmm. Now it's very good that you started because this is light, right? We have, what is it? We go from, say, 400 to 900 nanometers. Blue, red. Now red starts at about 590. That's already red. So if your manufacturer sells, we have a red fluorescence filter. Well, what do you know? Nothing, because it could be this, it could be this, and it's still red. So if you dye fluoresces like this filter, which is a red filter, will give you a very poor signal, where this filter will give you a very high signal. So sometimes you lose light and you don't know why it is, hey, I have a red filter, I have a red fluorescent dye, I should be seeing it, I don't see it. It could be because you need to look for a different filter. They will not tell you. If you buy a machine, the manufacturer will not show you the problem.
Con las extensiones, por ejemplo, o queréis ver otras cosas, tener lo que haces tú, si queréis separar el grupo específicamente, ahí ya te sirve.
Ahí sí, pues. Pero en forma nativa, así.
No, tengo grupos generales, pero incluso ahí tú podrías hacer un poquito de filtro más angosto del que puedan ver las personas y podrías separar.
So we have two things. We have a mirror, a dichroic mirror, a mirror that reflects light in one color. So if you had a dichroic mirror that, say, splits at 650, we had one, right? It's 650 long pass. Then reflection, or what passes through the filter, is this. And what is reflected is this. 400 to 900. And at 650, this is the pass light, and this is the reflected light. Then there's what we call a band pass filter. So we could have let's say a 700 band pass. That means at 700 nanometers it will pass a band of colors. You need to know how wide it is. There's a huge difference if you have a band pass filter like this or a band pass filter like that. So they usually say, well, it's 10, 710. That means that the width is 10 nanometers. So normally you would do, with a mirror, you would split the light in long and short wavelengths, and then you would choose with a band pass filter, you say, I only want this to see that color. And with another band pass filter, you get that color. Now what would happen if I put this filter here? Two filters that work very nicely. Now I see nothing, because this filter stops everything, so that filter sees nothing. That happens so often. You have two filters and you put them in the wrong channel, and you're totally lost, and then you start skimming around, and then a little bit of light leaks through, and suddenly you see a little signal, and you start focusing, and it becomes stronger and stronger, and then you say, that's funny, the whole machine used to be totally different. And that's because you now optimized it for a wrong filter combination. So knowing your filters and knowing what's in there is very, very important. Also to know the chromatic properties of these filters. And sometimes you don't know them, so you take 4 or 5 filters and you try them out and see which filters give you the best results. Again, in medical equipment that's not important, because the equipment makers for medical tests know what dyes you use. But if you work with dyes that you don't know, and you only know that it's a red fluorescent dye, and you have a red band pass filter, it doesn't really tell you that much. So.
I have a question. When you pass a cell,
Yeah.
and you have one cell that could have any dyes,
Any color.
Yeah. So you use a filter.
Yeah.
To, for example, if you first said I want to see all the red cells, for example.
Yeah.
And then you choose the cells that are red.
Yeah.
Or you know, or you detect what color is that cell.
You detect what color.
Ah, okay.
So if I have a mirror and all the red goes here and the green goes here, right? So this is a mirror that splits the light into 2 regions. So red and green go in.
Oh.
This is the signal from a cell. And then I get 2 channels. I say the red light goes there, green light goes there. Then I have 2 detectors.
2 detectors. Okay.
And now I can say red, green. Yeah, I can say, so if there's a green cell, this detector will do close. This detector will do nothing. If there's a red cell, I get a pulse, I get nothing. So if an event happens, I say, okay, this is 100 unit green, 10 units red, 10, 100. That's where the cell is. And now the other way around, the cell is there.
So you can identify, for example, orange.
Yeah, and then I can do a third axis and it's orange.
Or in the middle of that.
No, third.
Oh,
And then a fourth, and I can do up to 32 colors.
Third?
Yeah,
Wow.
so I could do 32
Detectors.
filter combinations. What do you think?
You can.
What do you think the chances that you make a mistake if you do 32 detectors? 100%. It's impossible to build, yeah. But, so you're not limited by the detectors. You can do this. You're limited by how you can think about space, because you cannot think about 32 parameter space, and by the proper filter combinations.
Nosotros tenemos 16 colores.
So when you see those dot plots, that's what it means. And so immunologists will say, okay, I know the red. That is a
T cell.
yeah, B cells or some antigen, I don't know. So they actually make it a binary system, because they say, well, this is a B cell and this is a T cell. And then you put this in a table and you say T cells, B cells, 37%, 10%, and you reduce your table. In oceanography you can do it because we don't know what the cell types are.
But you know that it's a population.
Yeah, but you saw that if you go deeper, they become redder and redder. So, if I take the cells from the ocean, I might see something like this. These are the deep cells and these are the shallow cells. So there's not a particular region where you can say this is this species or that species, because you may find the species at 100 meters there, and at 10 meters you might find it there. So the whole idea that you have in medicine, that there are binary systems and regions where you find something, is not necessarily true in oceanography. This is good. We got this? You understand this?
Can I add something?
Sure.
Sí, como tú tienes nomás que no te vas a ver, ¿no?
En esta combinación, lo importante también es que tenemos que saber que las longitudes de onda van de mayor energía a menor energía. Entonces, esto tiene que ser en bandpass creciente. Tú no podías, si haces un filtro, ya perdiste todas las longitudes de ondas menores. Entonces, si tú pones un bandpass filter, pues este es un filtro general. Entonces, esto te dice que todo lo menor a 488 lo refleje, no haga scattering. Entonces, y le pone un band pass filter de 488, quiere decir que toda la luz menor a 488 va a rebotar, y acá tú pones un filtro que va a detectar 488 más o menos cierta longitud de onda, y eso va a un detector. Entonces, todo el resto de longitudes de onda mayor a 488 siguen en el camino. Acá tenemos un nuevo split que también es para polarización, pero si llegamos acá a un filtro long pass 550, todo lo menor queda acá y pasa solo lo de 550, y acá tenía un long pass 650, entonces todo lo mayor a 488 y menor a 550 rebota, y le pones un detector acá con un filtro acotado a una longitud de onda y lo detectas, ficoripina. Todo lo 650 superior sigue, y acá le pones un band pass filter para clorofila y tenéis solamente lo de clorofila. Entonces nosotros vamos a ver en el equipo, tenemos un bloque largo con distintos espejos y filtros, que es exactamente esto mismo. Entonces, para que tengan claro que...
Y que sea polarizado, ortogonal o paralelo.
Eso depende de la polarización de la luz, que lo vamos a ver después con Engh en un capítulo aparte, que es un poco más complejo.
Hay parte también el forward scatter, con lo que lo
Sí, pero eso lo vamos a ir viendo. Yo creo que con la práctica va a ser más útil cuando veamos los bloques.
Yeah. So, any more questions about this? No? So now we have pulses. So there's a signal here. remove the light by spatial filtering to the pinholes, and now I get it on the different detectors. All the detectors at the same time go, whoa! But that doesn't mean anything, because you know, it's still electrons, and we need to now get it ready for a computer. And I'm going to talk about this very quickly, but there's a few terms that you may want to know. The pulses, you can measure the peak, you can measure the pulse width, and you can measure the area. Sometimes those mean different things. In the electronic circuits, you use a peak sample hold and an analog to digital converter. So we start with an analog signal. The fluorescence is this high or this high or this high, so the brightness. But if you want to do it in a computer, you have to write it down. Okay? You have these events, then a peak sample hold will determine how high the peaks are. And then the analog to digital converter will say, this is 10, this is 17, and this is 35. So we will go from a signal that's proportional to the fluorescence to a signal that you write down. And once you got the numbers, the computer can do something. So that's an ADC. Asynchronous. Asynchronous.
Yeah, hear it.
No, why would I put it in there? What was I thinking? Oh yeah, we can look at different sources and see if they're at the same time or at different times. That tells us something. And then we have digital versus analog. Very few people, and Victor, you know that very few people nowadays can do analog electronics anymore. They're all working digital. And they cannot do proper handling of the analog data from photomultipliers. It's really very, very sad. Actually, computers have become so difficult because all the circuitry is on a chip now that nobody can build digital circuitry anymore. They all work with controllers and stuff, but nobody can build a nice digital circuit anymore. We are a dying breed, Victor. We are a dying breed. So this is the pulse. So we could measure how big it is. Well, how big is it? It's like just how big is a human. There's several things that you can measure. What's the right measurement? We could look at how high it is. We can look how wide it is. Makes a difference, you know. If you have say a long object coming by the laser beam, then the signal will look something like this. It comes in and then it goes out. If you have a small object, it may look like this. The height is the same, but the width is not the same. So we can ask that question. And if you have, say this, the width is the same, the height is the same, but now the area is different. So the three measurements, the height, the width, and the area, can indicate different aspects of a phenomenon. And electronics can do that. You can have built electronic circuitry. The pulse comes, you say, okay, how wide was it, what's the area, and what's the peak height. You can do that analog, and you can do that digital. Analog, so here we go from a height to an analog to digital converter. So the analog to digital converter will say it's this high, that number. So say this is 10 volts and this is 5 volts. And the A to D will say it's 10 volts. Or I can continuously digitize it and then say, okay, give me this number, which is 10. And then of course, or I could take all the numbers and could add them up and then I get the area. This is much more accurate than this, because very fast digital electronics just are not precise. They have a lot of noise. But all machines nowadays do it this way, because it's so simple. Nobody knows how to build analog circuitry anymore. Only the very best people know how to do that. So a lot of the modern cell sorters and digital electronics and they are horrendously inaccurate. Not very good. Now we have another problem, because we have a pulse, right? And the pulse is only 1 microsecond. But there's light in the room, and there's a background of about, what is it? What do you have in Chile? 60 hertz or 50 hertz electrical? 50. So there are other signals that are being detected that because of the lights in the environment or other things, but they're all a lot slower than 1 microsecond. 50 hertz is like the video frame. There's stuff happening very slowly and there's stuff very fast. So you build electronics that can only see the fast stuff and not the slow stuff. So that's called baseline restoration. So we want to know this difference. We do it, these two pulses are the same height if I would do an absolute measurement, but if I measure this with respect to background, then I see the true height of the pulse. That's called temporal, also a form of temporal filtering. So I'm just telling you that because electronics may make a difference. You know, you don't think about it. You have a box and you say, okay, this is what the computer tells me the number is. But maybe there's ways to there's a different number. Maybe you're looking at the height and you really want to know the pulse width or something like that. Yeah. So you need to understand a little bit of that. And then, you know, this is not really a good slide. I'm going to skip it. Now here you can see how important it is. This is when we started. These are one of my first results with ocean samples. This is Prochlorococcus, Symptococcus, Pico, eukaryotes. So here you see, you now understand what that plot is. This is the signal on the scatter detector. That's the signal on the fluorescent detector, and this is the noise. See, so this is the scatter noise, and I can only see Prochlorococcus if I also look at the red signal. If I would not have the red signal, this would go down and it would be among the noise. After we've been playing with scatter signals a little bit, we got Prochlorococcus out here. 1, 10, 100, 1,000. Now suddenly Prochlorococcus is about 1,000 times more visible than noise. So tuning an instrument and really trying to understand what's going on can be very, very helpful at times. These are calibration beats, half a micron calibration beats. They're off the scale. The noise is down there. Now this requires very, very careful alignment of the machine, and you really need to know what you're doing, but it is possible. It's always possible. If you have an object that you cannot see, you can always favor the condition of your instrument, the electronics, the optics, and what have you, to focus in on that phenomenon and pull it out of the background. And you guys have this detector, this small particle detector. Gotta skip it.
Come on.
What?
You will skip the...
Well, this has to do why you need a large dynamic range, because if you have particles, 200 nanometers, 10 microns, still very small. You know, if we would look at them and say they're all very small, then the scatter covers an enormous range because of light. You know, this is the wavelength of light. If you have a particle that is this big, or a particle that is this big, it's only maybe 5 times smaller, but it interacts totally different with light, because the light is such, it's like having a comb that you use for your hair. I don't use them a lot, but you can tell me they exist. If you had a very small particle, you could comb over it, and if the particle is just 2 times bigger, you suddenly move them. And that's kind of what's happening with light. Light is kind of a grid, and it's about the same, so some particles you may pick up very easily and other sizes not. So for that reason, we need a high dynamic range. Because of that, and I'll just remember the names because you're going to see them. If the particle is much smaller than the, or much bigger than the light, then we talk about classical optics, Newtonian optics, refractive index optics. There the signals are proportional to the square of the diameter of the particle. Understand that? So if you have a particle of 10 micrometers and a particle of 20 micrometers, the scatter refractive is the size squared. If you go to the size where the particle is about the wavelength of light, you have me scatter. Me was a person who for the first time did the mathematical analysis, and it goes with the fourth power. So if we go to 1 micron, and or say half a micron and 1 micron, which is still 2 times, this suddenly becomes 2 to the 4th, is 16 times. So there you go down a factor of 2, and you get a signal that's 16 times weaker. If you go to Rayleigh scatter, Mr. Rayleigh lived around the 1800s, one of the people I admire most in science. He was a mathematician, but he liked physics, and he was just sitting with his candlelight. There was no electric light. At night he would be sitting with a candle and calculate all these things, and he would calculate what the scatter would be from very small particles. Can you imagine it? You're in an age where there's no electrical light, no computers, nothing. And you think about the problem. If I had a light wave this long, you could imagine that, and I have it interact with a very small particle, what would happen? And he predicted that for very small particles, the scatter would go to the 6th power. So now suddenly this is 2 to the 6th, which is that 32? 32 times. So as the particles get smaller and smaller, it becomes harder and harder to measure them accurately. Rayleigh scatter, by the way, is why the sky is blue. Do we know that?
64.
2 to the 6th? Are you sure?
4, 8, 16, 32.
Oh yeah, 32 is 5th, yeah, 64, so 64. It's even worse than I said. 64. So Rayleigh scatter is why the sky is blue, because molecules of air are very, very small. So the scatter is very, very little. But the wavelength is a factor 2 different. So if you have a very small particle, because it's the diameter of the particle with respect to light. So blue light is half the wavelength of red light, but the scatter from blue light is 64 times more than that of red light from the same particle. And that's why you see the blue scatter from the gas molecules, and you do not see the red scatter. So the blue sky really demonstrates that Mr. Rayleigh was right before he even knew what he was talking about, because he never imagined that that is the case. But also shows you the power of theoretical mathematics. Unfortunately, everybody now with mathematical interest becomes a computer programmer, which is totally uninteresting. You know, the real interest is in pure mathematics, because that actually gives you useful results. Pure science gives you really useful results. And here you see it, you know, this is the scatter of particles, and it's nonlinear. You cannot tell from the scatter how large the particle is, because there's the first component, and that is refractive index, and that is very hard to catch. It's not a thing, you know, a lot of oceanographers take calibration beats, and they say, okay, my calibration beats are 1 micron, that particle is 1/10, so that must be 100 nanometers. Do it so that everybody can see it. Everybody look at Carlos.
It's not true.
Not true, exactly. This irritates me so much that this, you know, you have these calibration
We
beats.
have the slide that we work in Seattle, not here. I use all the...
Oh yeah, he did some experiments on that. Now I don't have the slide in here, but yeah. So it's very, very difficult to, when you have a calibration beat, to
Assume.
yeah, and in fact you see, I think these two particles are different, but they have the same scatter. And that just happens how, you know, how they interfere with a particular wavelength. And if you use another wavelength, they may all move. They may all move. So you can never, this is a very precise machine. Machines says, oh, this is like a very precise scatter, but the position of the peak is not related to the size of the particle directly.
And these are also regular particles, spherical, perfect peaks. It's always more complex.
Yeah, and, well, it's here you see this looks like the two particles, this is actually one sample, but there's two particles in there. So you never know. You never know how it works. But I see it a lot. I see a lot of literature, especially oceanography literature, to say, okay, this is a 1 micron particle. There's another micro prochlorcoccus, so that would be 1.5 microns. Nonsense, nonsense. Paper should never be published. Should be rejected. And this you cannot really see, but this is to show this is the smallest particles we measured. These are about 100 nanometers. And 100 nanometer particles, 200 nanometer particles.
It's a really nice resolution. Ustedes quizás no lo toman en cuenta, pero tener ese nivel de resolución a nivel de 100 nanómetros lo hace un solo grupo prácticamente, que son los amigos de ellos que trabajan en Holanda. Tienen una súper buena resolución con el citómetro y pueden ver un pic claro a 100 nanómetros. Ustedes pasan una muestra en un citómetro convencional de 100 nanómetros y solo ven ruido. Entonces, para que tengan en cuenta que este citómetro tiene una potencia increíble y que aparte si tiene una buena óptica y buenos detectores, tú puedes llegar al nivel de resolución que está mostrando bien en esta figura, que no es trivial tener ese tipo de señal a tan baja. 100 nanómetros es, no sé, el láser azul es 480, el láser UV es 355, estamos hablando de 100 nanómetros, realmente pequeño.
Yeah, and this is very interesting. So I built machines that were sold commercially, right? So we sold this machine to a group in Holland that was doing blood cell research. Then I developed for oceanographers a detector that could see very small particles. The people in Holland said, can we try it? And they suddenly saw small particles in blood. And now the whole lab is working on small particles in blood, which nobody else ever worked on. And they're now the leading group in the world, because they're the only group. They're not particularly smart, but they happen to be very lucky and use this detector. So a lot of the stuff that you develop depends on the samples you work with. That inspires you, that makes you make certain technical improvements. But then you find, once you understand what you have been doing, that other people can use it and be successful. And that happens a lot. In fact, what?
Ger Artestein.
Ger Artestein, yeah, here, Ger Artestein.
Oh.
Ger Artestein in Utrecht.
Can you see virus?
Well, there are people that claim you can see him.
Okay.
You're not sure.
I'm not sure, because the data don't look very good to me.
But that kind of resolution you
But,
maybe can see.
yeah, so I'm now working on even better scatter detectors. I hope that we really will be able to do things like that and have some confidence that what we're seeing is not an artifact, but it's really real. Because in the ocean,
You can find.
viruses are the most important thing, right? If you're a virologist.
Yo creo que mucha gente, tú puedes encontrar artículos científicos que dicen que detectaron virus y cuentan virus por citometría de flujo, y tú ves la figura, tú dices, ¿cómo esto es virus? Es básicamente ruido.
Yeah, you get a plot, yeah. You know, you see dots everywhere, and then they put that on cells, and they say, we think there is 100 viruses in there. These are 100 dots, must be virus.
But you can separate it and maybe you can see microscope.
I'll tell you something. I'll tell you something. All the virus work is not done on the sorter. It's just a flow cytometer.
Oh, no.
So yeah, you should do that. It's all, but it's been going on for about 10 years. People, there's a group in Holland again that they say that it's viruses. I don't know. I'd like to see better experiments. You know, the best thing to do is to sort and look at an electron microscope, right?
I tried with Peter. Doesn't work.
Well, that doesn't mean the same. You guys cannot make it work. That doesn't mean the same. This is to show you the dynamic range. This is over 4 decades. This is what 8 peaks, sphere techniques, counting. Do you use those beats? 8 peak beats? So there's 8 peaks. 1, 2, 3, 4, 5, 6, 7, 8. Something very interesting is happening here. These peaks are high, these peaks are lower. Do we understand why? Not a fair question, but if you do a measurement, if I have a fluorescence of 100, what would I measure? 100 or 99 or 101? Well, sometimes you measure 101, sometimes you measure 99, right? So even if it is 100, you will not see 100. So this is a good thing to worry about. Yeah. So this is what I shoot. The expected answer, the right answer is 100, and I might get that, but sometimes I have a little more, and sometimes I have a little that. So if you really have every particle has exactly 100 photons to you, 100 photons, you would see this. You would see a Gaussian curve, right? 100 photons will give you a curve that sometimes gives you 90 and sometimes gives you 110. Does anybody know what happens if it's a discrete problem like that? You have 100 photons. What the width of the curve is? Sampling error. Everybody go. Square root. So this width is square root of 100 is 10. That's if the only error. This is the only error, now is the sampling error. If I have other errors, so this is my sampling error, I have another error, which is 20, then you get error 1 squared plus error 2 squared plus error 3 squared, and the square root of that is your error. But if my sampling error, and you can never get better than your sampling error, is the only error, then you should expect the square root of the number. You get that? And this is important because we are only sampling, and nobody realizes that, or very few people realize that in flow cytometry you only get 50 photons, 300 photons. And that's exactly what you are seeing here. This is 10,000 times brighter than that one. So the square root of 10,000, what is that? 10,000 is 100. So my coefficient of variation is 100 divided by 10,000.
0.01.
0.01? Is that it? And
Yeah,
what is, so this is 10,000. What is this? This is 10. So, right? 10. And the square root of 10 is about 3. So here I have an error of 30%. Yeah, that's big. So here I'm very precise, and I'm here very inaccurate. So since the number of channels is the same, this will be a very sharp peak, and this will be a wide peak. And the way that these peaks get wider tell me whether I have a sampling error or whether another error dominates. If the sampling error dominates, I get this curve. Should be a straight line. If there's another error, I get a flat line, because the error for the measurements is the same. So this is the precision of the electronics here. This measurement I could improve by making better electronics or by reducing the noise of the laser. Here I'm dealing with sampling error, and I can only improve it by getting more photons. So the shape of this distribution tells you if you have 8 peak beats, whether you have sampling error or instrumentation error. This tells me that for this machine, which is a very good machine, because I built it, that the sampling error is dominating up to that point. So the only way that I can improve this is by getting more light out, which for an oceanic particle you cannot do. You can only get more rays out.
But that depends of the fluorescence, because it's a channel, you know.
The fluorescence it depends in the amount of fluorescence.
Yeah, so this is the amount of fluorescence, but it's plotted on a logarithmic scale.
8 peaks means that you have bits that have different amounts of fluorescence each bit. It's a mixture of bits that have 10 particles with fluorescence. It's a spherical synthetic bits that have in this small fluorescence particles.
So when I look at calibration data, they often say, oh, this is 10 units or 100 units, oh, that's fantastic. I look at how these peaks go down.
Eso lo vamos a ver en
And it tells me whether you have sampling error or not.
We will try 8 peaks in
Yeah,
there.
you should see this after. See, this is why I like projection and not television screens. It's like if we would have projected on that side, and I would have done this.
We have a pencil.
People would.
We have pencil and.
People would be quite upset, I think.
One question, the chlorophyll in a cell.
Yeah.
What kind of fluorescence have?
Well,
A lot?
yeah.
Or
Always.
or you have a spectrum of?
Well, you saw the graphs, right?
Yeah.
And this was prochlorococcus.
Yeah.
If I have a bead, it's there.
Oh.
So, is it sampling error in prochlorococcus? No, because then it would be this wide. Is it machine error? No, because then you can measure that accurately. It must be the natural variance of prochlorococcus. So that is why it's important to know. Is this the real variance of prochlorococcus, or is it my imperfection of my machine? The calibration piece can tell you. Let's see if I can find that. Oh yeah, here. See? Here we have beads, very, very tight. Here we have prochlorococcus. The prochlorococcus is 10 times more than the accuracy of the instrument. Not sampling error, prochlorococcus really is that variable. Now, does it really mean there is 10 times difference chlorophyll in different? I don't know, because fluorescence is not linear, but that's a different story. But here I can make an estimate, compare the accuracy of the machine with the accuracy of my measurement. And that's one of the reasons why I don't quite trust the virus data, because they never show anything like that. When they show their beats, they are about the same as what they think viruses are and stuff. And they say, well, can you really see that with instruments that are that inaccurate? I hope that you also realize that there's a lot of things that you can learn about your instrument and that can really help you improve the interpretation of your biological data.
Yeah, for example, you can know if you have subpopulation of prochlorococcus, for example,
Yeah.
with different intensities, for
Yeah.
example.
Yes, you could. If I look at this, I say, oh, I don't see it.
No.
It's just one, but yeah. But yeah, you need to be able to interpret these data. But this means that everything in the electronics, the sample hall, the amplifiers, everything has to be accurate within this variance. The laser cannot have noise. If I have a laser that is just adding a lot of noise, then it won't see it either. So all these things kind of are important indicators of what's going on. Let's see. And here we see it for different channels. So this is for the propylium iodide channel, the fluorescence channel, the FITC channel, the phycoerythrin channel, and the PH5 channel. You see that the same 8-peak beats now give you different different profiles. Here you see that we have sampling error all the way through. Here we are not limited by sampling error anymore. We have so much light. I said you can only improve it by getting more light. Here we have enough light to see these intensities, but here we could do better here if we increase the light intensity of the instrument. you also see that these peak shift, because although they sell them as white particles, they fluoresce everywhere, they don't. They have different dyes, and the peaks shift with respect to each other depending on what color of fluorescence you look at. And let me, why did, okay. So, let me quickly look. I forgot what's in here.
We can go through the sorting tomorrow, I think, or you wanna do it now?
The what?
The sorting part.
Yeah, yeah. So I guess that's why this slide is in. It's already almost noon, so we should very quickly go to the rest of this talk. But so this was the analysis part, right? We can do a lot about improve analysis. Now we're going to sort into different directions. So we're now going to say, okay, there's a cell. I want every cell that's brighter than 7 and dimmer than 12. And now if I see a cell like that, I tell the machine, put it into 2. And again, we go from an analog signal to a digital signal. Then there's a computer somewhere that says the digital signal is this big, and the computer says, is it bigger than 7 and smaller than 12? And if so, then the computer will do that. This is how it's built. So we have different. Again, you don't have to know this. If I ask you to make a drawing, if I would do a test, I would not ask you to make this drawing. This is how it works. We have detectors. Detectors give pulses. We have a delay line because we have multiple lasers, so I get a pulse, a pulse, a pulse, a pulse. I need to say, okay, if you see something, then so many seconds later you should look at that detector because that's the same particle. It's like you have 2 policemen, and one is measuring the speed of the car, and then he said, in 10 seconds there's a car coming, and write a ticket for him. But this is much nicer. This is nice, you don't get a ticket. So we have a delay line. So we say, okay, event happens. So many seconds later, you have to look. Then there's a peak sample hold circuit. Pulse comes up. You determine in analog domain. You determine how high the pulse is. Then there's an A to D converter. Those are going. All these values go into first in, first out buffers. So now I get. This is the cell that I see now. This is the cell that came before. If you look at the bottom value in the first in, first out buffers, I will not go in details, then all these values should belong to the same cell. And then I clock them out to a computer. The computer then sees the values of one cell that may have happened at different time points, sees all the values. We can have, say, 16 different measurements, 16 colors, scatter, what have you, area, peak. And the computer looks at the 16 values and says, okay, it needs for value 1, it needs to be bigger than 7, yep. Value 2, it needs to be smaller than 3, yep. And when the computer says, yeah, all these measurements are okay, then the computer tells the instrument to, when the next drop happens, to deflect that drop. And it looks, okay, looks like we have all that stuff. Yeah. I'm not going to show this. So now we can put sinks in different wells in different places, and we can get a subset of particles that we know the physical parameters of, but we don't really understand the biology. Now we can put them away, and we can determine what the biology is, so then we can correlate the biology with these measurements. I want to finish with a very practical application. This is done by 2 friends of mine, Jan Bayer and Ahmed Smit. They actually both worked in my lab at different times, and then they met each other after they left my lab and started talking to each other, and they actually fell in love. So Jan, who is a very creative guy, did this experiment. He put E. coli on a plate, an agar plate, and put 1 E. coli, 1 bacterium at each location. And you can see here that the seating efficiency is 80%. So this is like permanent. We have a plate, we put agar on, you put them on there. But he did something else too. He put fluorescent protein in the bacteria. And he could control where he puts the various places. So if you take this plate and you put it under ultraviolet light, you see Jan and Annette Bayer-Schmidt. So it was his love declaration to Annette, saying, here Annette, here's your sorted cells. When she went to the dark room, she saw both their nationals, and they're now happily married and have 2 very nice daughters. So, flow cytometry.
Love cytometry.
It's what Latino people. This is the perfect technology for the Latinos. And now we're going to talk drop formation. These are my 2 cats, and this is the tap, and you see that when you make a stream of water, it does not want to be a stream, it doesn't want to be a cylinder, it goes, naturally it breaks into drops, which cats find fascinating. But I think we should stop here and maybe pick this up later. Shall we do that? Break for lunch? Any questions? No? All? Okay.
Juntamos a las 2, ya que vamos a adelantar un poco el almuerzo. Nos juntamos a las 2 y como dijo Guillermo nos dividimos en 2 grupos. Ustedes decidan 5 y 5. Y para optimizar el tiempo podríamos la mitad del grupo que se quede acá tratar de preparar su presentación breve, 1 o 2 tiempos a mañana y el resto está trabajando y ahí hacemos cambio.
Una cosa, es que hay gente que a lo mejor no trabaja nunca con cosas de citometría.
Bueno, pero independiente, por último, no con el citómetro, pero mostrar una manera positiva de lo que está haciendo.
No, es un alcance.
No, sí, por eso. Y si no ha trabajado en citometría, es como qué es lo que está haciendo, qué es lo que quiere hacer y cómo podría el citómetro ayudarlo en lo que está haciendo. Así de simple, no más de 2 diapositivas. Yes? We prepare one group of slides, one group working the citómetro.
Yeah.
A las 2 acá entonces.
Sí.
Cool.
Un aplauso, yo creo, como mínimo. No puedo aplaudir porque tengo la cámara, pero... Voy a apagar nomás.
Sí, gracias.